Good morning. Aubrey, can you hear me? I fell off for
Yes,
just
I
a minute
can.
here. You can hear
I
me?
can hear you.
Very good. I'll get started then. Good morning and welcome to Iowa State University's Carbon Removal Forum. I'm Robert Brown. I'm the director of ISU's Bioeconomy Institute and one of the organizers of this forum. Conceived 2 years ago, delayed by the COVID-19 pandemic, this forum is proven to be very timely. Carbon removal is receiving considerable attention in the US, as illustrated by this recent timeline. January 27th, President Biden's Executive Order 14008 highlights the potential role of agriculture in sequestering carbon in soils and the sourcing of low carbon fuels and bio-based products. February 2nd, during his confirmation hearing, Secretary of Agriculture Tom Vilsack remarked that there's an opportunity for us to create new market incentives for soil health, for carbon sequestration, for methane capture and reuse. February 11th, I learned that Elon Musk, who recently launched the X Prize for carbon removal, and I have a common vision for the ideal carbon sequestration agent, which he shared during an interview on the Joe Rogan Experience podcast. You want it to be something that is going to be stable in solid form for a long time. I don't know, make a cube of it. Just a giant cube. Go biochar. Now that's an exclamation is an editorial comment on my part, but let me continue. March 5th, in an interview, newly appointed Energy Secretary Jennifer Granholm noted that, quote, the Intergovernmental Panel on Climate Change has said that you can't get to net zero carbon emissions without carbon capture, utilization, and storage. We are excited about that, end of quote. So are we. But I would like to clarify, carbon reduction is the act of reducing the rate at which carbon dioxide enters the atmosphere, something the world has been talking about for a long time. In contrast, carbon removal is figuring out how to extract 410 parts per million of carbon dioxide from the air, concentrate it, and store it for a long time, a very long time. Both reduction and removal are important societal challenges, but our primary focus today is carbon removal. As you can see from the Do the Carbon Shuffle slide, there are many possibilities. We are especially interested in approaches that harness agriculture to achieve the ambitious goal of carbon removal. Next slide, please. As you can see from the agenda, our forum includes 2 distinguished experts and panels of faculty and students to help us understand the topic. The organizers of this forum are gratified to have several leaders of Iowa State University join us today, who will also address the forum. Next slide. Before kicking off our program, I would like to remind everyone that the forum is being recorded. President Wendy Winterstein, who is Dean of the College of Agriculture and Life Sciences, played a prominent role in establishing the Bioeconomy Institute, has taped a welcome to our participants, which we'll run now.
Good morning. I'm pleased to add my welcome to the Carbon Removal Forum at Iowa State University. I want to first recognize and thank the team at ISU's Bioeconomy Institute, including Director Robert Brown and Associate Director Lisa Schulte-Moore, who also directs Sea Change, the consortium for cultivating human and naturally regenerative enterprises. Thank you for your leadership in organizing this forum and bringing together the ISU community for these important conversations. I also want to welcome and thank our special guests, Dr. Philip Robertson from Michigan State University and Dr. Daniel Sanchez from the University of California, Berkeley. Thank you for joining us and for lending your expertise and partnership to the important issues of carbon reduction and removal. Iowa State University is a proud leader in science and research to advance agriculture, engineering, and innovative solutions to mitigate climate change. We know that no single expert or discipline alone can address all of the complexities of climate change. That is why having a forum such as this is so important and so necessary. Effective collaboration begins with conversations. This forum is a wonderful way to establish a common understanding of carbon reduction and removal. Just as important, it's an excellent opportunity to engage diverse voices and perspectives and to hear from those who have not been part of the conversation before. We know there is great power in collaboration. The best strategies and solutions are born when we add more voices to the conversation. This allows us to leverage our top resources, our best minds, our science-based data, and our groundbreaking research. Together, these resources create powerful impact. We are excited and encouraged by the incredible potential to advance the bioeconomy, to grow, diversify, and create added value for agricultural markets, while ultimately creating a more sustainable future. This is an important priority for the state of Iowa. A thriving bioeconomy is vital to future growth and prosperity. Thanks to the excellent work occurring at the Bioeconomy Institute, Sea Change, and other units across campus, Iowa State University is at the forefront of these efforts. This is a shining example of Iowa State's land-grant mission in action, bringing together dedicated individuals to tackle complex local and global challenges by creating, sharing, and applying new knowledge. I appreciate all of you for being here today and for making this a priority. Your work is important, not just for Iowa State University, but for all of Iowa and the world. I look forward to the strategies and next steps that will come from today's conversations and the momentum it will build for this important work to continue. Thank you, and have a great forum.
We appreciate President Winterstein's remarks. Senior Vice President and Provost Jonathan Wickert has joined us this morning and accepted our invitation to address the forum. I'm proud to say that I've known John since he joined ISU in 2007 as the chair of the Mechanical Engineering Department, which is my own home department. And he went on to serve in several impactful roles at Iowa State University. John?
Great. Well, thank you very much, Robert, for the kind introduction. And I also appreciate the opportunity to join the Carbon Removal Forum this morning and add my own personal welcome to that of President Winterstein. I especially appreciate that having programs like today's forum, even while still in a virtual Zoom online format, really makes it start to feel like we're beginning to turn the corner in our recovery from the COVID pandemic. And I'm also delighted that this virtual format has enabled so many to join today's forum. I'm very delighted to see the broad participation from many different organizations, experts from all different disciplines. And it really is that interdisciplinary approach to this critical topic, I think, that makes today's forum so timely. Today's forum comes at a very unique time for Iowa State University, as well as for our nation and our world. Iowa State University, through the Bioeconomy Institute, through Sea Change and other entrepreneurial programs that we have, has long been a leader in both mitigating the effects of climate change in agricultural settings, as well as testing and commercializing processes that make doing the right thing very much worth that effort. I would also like to say the Bioeconomy Institute continues to be a very critical and important part of Iowa State University. And I'm very appreciative as a colleague, as a fellow engineer, and also as university provost of Dr. Brown's leadership for the Bioeconomy Institute and vision over the years. It truly is a gem of our university and our state. And really his entire team. You know, the Bioeconomy Institute continues to innovate and apply technology to important, challenging problems, including today's focus on carbon renewal. And this is exactly the kind of work that should be done and led by a land-grant university and a University of Science and Technology. So I very much appreciate the entire BEI team. I did mention commercialization, and I'm also pleased that we're addressing the economic aspects of these emerging and evolving technologies and discoveries. Commercializing technology and incentivizing critical land use management practices really will increase the rate at which we'll be able to change and protect our environment. I would look to wind energy as an example. You know, it really was not that long ago that wind energy was a boutique technology, renewable, exciting, but not always economically viable. Today, of course, wind, particularly here in the state of Iowa, is a leading energy resource and a thriving industry. And I truly believe that carbon removal offers very similar potential, both from the technology and economic perspectives. And really, this is how innovation, this is how land-grant institutions are supposed to work. And today's program is excellent and further proof of that spirit in action. So again, my appreciation to Dr. Brown and Dr. Schulte-Moore, as well as our guests from so many different organizations. I also saw that we have some folks from my alma mater, UC Berkeley, joining us today as well. So I wish you all a very productive forum and impactful discussions. And thank you again for the opportunity to join you briefly this morning.
Much appreciated, John. Thank you. Vice President of Research Peter Dorhut arrived on campus in January from Kansas State University to begin his new role leading the research enterprise at Iowa State University. Happily, this occurred just in time for him to participate in our Carbon Removal Forum. Peter has agreed to provide his perspective on the potential impact of the challenge of carbon removal on interdisciplinary research at ISU. Peter?
Thank you, Robert, and thank you, Lisa, both of you and your team for putting together a fantastic forum. Thanks to Professors Robertson and Sanchez for joining us today, and of course all the faculty and the students that are participating in the forum. You all are the ones who are involved in the critical conversations that are going to help with our understanding of not just some of the challenges, but some of the opportunities that are in front of us. Now, I'd like to go back a little bit farther in the timeline that Robert shared with us. Let's see, where shall I begin? Why don't we go back about 10 to the 9 years? Now, I'm a chemist, and I love thinking about, one, thermodynamics, and number two, big numbers, because those big numbers are things that we're going to have to grapple with. 10 to the 9 years ago is roughly when photosynthesis began on this planet. And just to give you a rough number again to think about, in any given year, we've got, thank you for the conversion factor there. In any given year, I'll throw out an even bigger number now. The sun provides roughly 10 to the 20th kilojoules of energy to Earth. Again, I'm a chemist. I love thinking about things in joules. Many of you, maybe there'll be a conversion that goes from kilojoules to BTU in a moment. But I think about this from the chemical process. Robert talked about how there's this goal of creating a cube of carbon for storage. Well, just to create a cube of carbon that's roughly 12 grams takes about 400 kilojoules of energy, right? That's the uphill Sisyphusian task that awaits us as scientists, and trying to reverse that particular process. And we can do it through a variety of mechanisms. I alluded to photosynthesis as the process. So when we think about that and our own human evolution, which began roughly 10 to the 6 years ago, you know, we didn't have the ability to photosynthesize. We lost that through the evolutionary process, and yet we survived because we figured out how to eat things that did. And then when we'd grown tired of eating things that did know how to photosynthesize, we began to eat things that ate other things that knew how to photosynthesize. And you can blame Prometheus for this, or you can blame early human creativity, that in roughly 10 to the 6 years ago, fire was something that we were able to begin to understand. And then we cooked things that ate things that photosynthesized. And we warmed ourselves so that we could live longer and cook more things that ate things that photosynthesized. The point of all of this is that we have grown through our process of as a human species of growing ourselves and getting to a reliance on this thermodynamic downhill reaction of carbon to CO2 and energy. And now with this comes a great challenge. The great challenge is, how do we take the phenomenal scientists and thinkers that we have in our midst today? Over 200 of you have joined us. And how do we take this grand challenge and turn it into something as a great opportunity? And so if I can paraphrase Stan Lee and Spider-Man, with great challenge comes great opportunity. And this is what we're here to discuss today, are the great opportunities to advance our understanding of how we can grab some control over this process that began long before any of us joined the faculty here. It's opportunities for students, and the president and the provost have already alluded to the fact that as an institution of higher education and an engine of innovation, we have an opportunity to engage students in this discovery process, this unique challenge, and this opportunity to really make a difference, not just years from now, but today. So again, thank you for joining in the conversation. Thank you for sharing your perspectives and your expertise. Thank you for the invitation to listen along and participate, and I'll spend as much time as I can today doing that. But enjoy, be creative, and remember thermodynamics. Have a good day, everybody, and enjoy the forum.
Thanks, Peter, for quantifying the challenge for us. Next, Lisa Schulte-Moore will be introducing our first keynote speaker. Lisa.
Hi there, everybody. I'm Lisa Schulte-Moore, faculty member in Natural Resource Ecology and Management and Associate Director of the Bioeconomy Institute. It's my great honor and pleasure to be able to introduce Dr. Phil Robertson, who's a University Distinguished Professor of Ecosystem Science in the Department of Plant, Soil, and Microbial Sciences at Michigan State University. Dr. Robertson's accolades are so many. I take the rest of the forum to list them all. So I'll just say that his positions, his grants, his publications, it's really quite phenomenal what he's been able to contribute, and so much of it is just front and center, addressing the topic of today's forum of carbon reduction and removal. I'll put his bio-sketch, a link to his bio-sketch in the chat, so you can follow that on your own time and learn more about Dr. Robertson. But for right now, I'm really excited to hear his talk. So I'll turn the floor to Dr. Robertson. Thank you.
Thanks so much for that kind introduction, Lisa. Let me start my screen here. Hopefully that's showing. So I am really delighted for the opportunity to speak today about one of the grand challenges of our time, which is, of course, adapting to and mitigating a changing climate, especially as it involves agriculture.
Sorry. Sorry to interrupt, Phil.
Okay.
I think your microphone might be really close, or something's going on, because it's really, I don't know how to describe it. It's very hard to understand you.
Okay, let me switch microphones here. Please
I
bear
don't know
with
if
me
I'm
for
the
a
only one
second.
experiencing that. Very sorry to interrupt.
That's okay. So is this microphone better? Does that work any better?
For me, yes.
Okay, I'll proceed on.
Sounds like, yeah, from the chat, people are hearing it much better, and so am I. Thank you so
Excellent.
much.
Yeah, thanks so much for interrupting me. I would hate to have gotten a quarter of the way through knowing that people weren't able to understand. So let me start over then and re-thank Lisa for that very kind introduction. And note that I'm really delighted for the opportunity to speak today to this group about one of the grand challenges of our time, which is adapting to and mitigating a changing climate, especially as it involves agriculture, which is of course, a slow moving, slow building and arguably existential threat that creates both challenges and opportunities. I've been working in this space for several decades now as a biogeochemist and ecosystem ecologist working in agricultural systems and landscapes, especially on the mitigation side, where I've spent a lot of time helping to work out the sources of greenhouse gases and field crops and their environmental and agronomic controls with an eye towards those practices we could engage to put a real dent in climate change. And that's what I'm going to talk about today. Opportunities for agriculture to make a positive, substantive contribution to mitigating climate change. And, of course, we don't have it all worked out yet. There are some areas of controversy and some frontier areas where there's yet unproven potential. And I'm sure there are areas that aren't even on the radar yet that will contribute in significant ways to this effort. But what I'll show today is what we know now about a few areas for which there is substantial agreement about the prospects, and provide some new numbers that describe the potential in the grand scheme of things. So let me start. Let's see if I can get this. Let me start with the big picture. What do we know with certainty? Well, we know with certainty that we're headed for a greater than 1.5 degrees C world, and a much warmer world in the absence of large-scale mitigation. We also know that even with aggressive mitigation, we're likely to overshoot 1.5 degrees C at mid-century. But with enough CO2 removal, we have a chance for keeping the end of century change at 1.5 degrees C, with any luck a little lower than that. Integrated assessment models, which are global models that integrate energy, land, economy, and climate systems to predict temperature change, have identified some 90 different socioeconomic pathways that have a better than 2/3 chance of keeping temperature change to 1.5 degrees C. And the IPCC has grouped these into 4 classes based on fossil energy use. P1 with its unrealistically low energy use, to P4 with its business as usual trend, to identify the amount of CO2 that must be removed from the atmosphere under each scenario. And guess what? All pathways engage agriculture in really massive ways. This is a graph of the P3 middle of the road pathway, the one that is most likely to occur if we act soon and fairly aggressively. It shows current CO2 emissions, around 40 gigatons of CO2 per year, declining to net zero by 2050. But because of overshoot, because of the excess CO2 that remains in the atmosphere at that point, there's this additional need to remove somewhere between 100 and 1,000 gigatons of CO2 by 2100. Now, I know these numbers, these units don't mean a lot to you out of context, although Peter Dorhout will appreciate them. I'll add a bit of context a bit later, but the important point here is that agriculture and forestry, this AFOLU term in the graph, together with bioenergy, specifically bioenergy and carbon capture and sequestration, are the only affordable and technically feasible negative emission technologies available today at scale. So, and these are, these will occur mainly through carbon sequestration, nitrous oxide abatement, and bioenergy. which I'll talk about in some detail in the remainder of my talk. But first, to understand the abatement potential, it's important to understand the sources and sinks of CO2 equivalents in modern cropping systems. And CO2 equivalents are simply a way of considering the impact of other greenhouse gases than CO2, methane and nitrous oxide in particular, in units that are common. And sources of CO2e, CO2 equivalents in crop systems include those in this bulleted list, which you can read, and you could probably make a list of this that would look very similar on your own if you thought about it for 5 minutes. But of course, all of these sources are not equal. By far the most important sources, as noted in this upper left-hand bar on this graph of CO2e sources from a corn, soybean, wheat rotation in Southwest Michigan, are nitrous oxide emissions, which are the purple bar, nitrogen fertilizer manufacture, that is the CO2 that is released when nitrogen fertilizer is created in with the Haber-Bosch process and a fertilizer plant in the Gulf Coast, and diesel use, the orange bar. Others are present, they exist, but they're not nearly as important as these. And these sources can be offset, at least for now, by soil carbon sequestration with no-till, as indicated in the second bar from the left, where the no-till carbon capture is represented in red. Can also be offset by carbon capture in cover crops, and the bar on the right, leading to net zero carbon farming and even net negative farming, as indicated in these lower bars, which are basically the sum of the upper and upper bars. So in the rest of my talk, I'm going to describe the 3 big mitigation opportunities in turn: soil carbon sequestration, nitrous oxide abatement, and bioenergy. I'll spend more time on nitrous oxide abatement and bioenergy because those are probably less familiar, at least in terms of the greenhouse gas mitigation potential or contribution to carbon removal than carbon sequestration. But I do want to, I need to cover carbon sequestration as well because of its importance, especially in the first half of the century. And then I'm going to put this in context against total needs with some coming back to the big gigaton CO2 numbers. So the basis for soil carbon sequestration as a mitigation strategy is historical carbon loss. Locally, upon cultivation, about 40 to 60% of the original carbon is lost in almost all soils. Worldwide, it turns out, but certainly in North America, after only 40 to 60 years of cultivation. And this has been known since early in the last century. This classic paper by Haas et al., which was published in 1957, a study that started some 45 years earlier than that, though, noted this loss. And one can calculate that globally, there's some 75 petagrams of carbon that have been lost from soils to 1 meter depth. And about half of this carbon has been lost from cropland and about half from grazing lands. And the implication is that there's a potential for recovering this carbon. We don't know if we can recover it to the original equilibrium level, how fast we can get there, or whether it will happen at depth to the same extent as at surface. But nevertheless, there is a potential for recovering a fairly substantial amount of this. And you can see on the map on the right that historical carbon loss in the Midwest, if we could effectively reverse that and turn that map into a negative, we would be well on the way to storing substantial amounts of carbon in soil. So how to restore carbon? Well, really, there are only 2 ways to restore carbon. One of them is to decrease carbon loss from soil, that is to slow decomposition, mainly through tillage reduction and manipulating residue quality so that the microbes don't eat it as readily. And the other is to increase carbon inputs to soil with cover crops, with changing the quantity of residue that goes in, and with additions of compost manure or biochar. And you can see work at KBS that illustrates these potentials in the far right carbon corner of this of the bottom table. The percent increase for different cropping systems, no change after 12 years in conventional tillage, but continuous No-till led to a 23% increase in soil carbon, similar to that for cover crops, and perennial diverse herbaceous crops really laid on to carbon. Of course, we can't eat those, and so they're of limited comparison for food systems, but nevertheless, for bioenergy systems, they turn out to be quite important. And there's still a lot to learn about soil carbon accrual. For example, we're only just now learning about the importance of root-created micropores in soil for stabilizing soil carbon. This is an X-ray microtomograph of a cubic centimeter of soil taken from a soybean field on the left and from a restored prairie on the right. This work led by Sasha Kravchenko at Michigan State. The light area are soil pores, not particles. And the differences in specific pore sizes appear to explain the much faster soil carbon accrual in the perennial system, which suggests a potential path for engineering annual crops to sequester more soil carbon. And this is one of several frontier technologies to keep your eyes on as we move into the next few years of research. So I want to switch gears now to talk about nitrous oxide for a few minutes and explain what we currently know about N2O abatement. First, understand that atmospheric concentrations of N2O have been increasing at a rate similar to carbon dioxide since the late 1700s. And this is noteworthy because although concentrations of N2O in the atmosphere are much lower than CO2, these molecules are about 300 times better at trapping heat. And one way to think about this is keeping a kilogram of N2O out of the atmosphere is equivalent to sequestering 300 kilograms of carbon dioxide. So you can understand the potential value of abating N2O. But also, unlike CO2, most of the atmospheric N2O increase is not industrial, but agriculture. Agriculture is responsible for about 85% of the contemporary N2O increase, with about 60% of this increase from soil microbes that are stimulated by excess soil nitrogen. The total annual impact is substantive. It's around 1.2 petagrams of carbon equivalents, but again, to put that in context, this compares to fossil fuel CO2 loading of about 5 petagrams of carbon in the atmosphere today. Now, nitrous oxide mitigation can be very difficult, in part because N2O is a hard gas flux to measure or predict. But it turns out that the best single predictor of soil N2O emissions is nitrogen availability or fertilizer rate. The lower right graph tracks N2O fluxes from a switchgrass stand fertilized at 8 different N rates, with the highest fluxes on any given date from the highest N fertilizer level. And it turns out that N2O fluxes are exquisitely sensitive to fertilizer N, with emissions increasing exponentially with fertilizer rate after crop nitrogen needs are met. You can see on the right here where N2O fluxes are impressively high, but only after corn yields have saturated. So more nitrogen added after 101 kilograms in this case, had no effect on yields, but the N2O emissions just skyrocketed. And this gives us a really interesting way to avoid excessive N2O losses without affecting yields. In this example from irrigated wheat at Summit in Western Mexico, you can see on the right that the optimal nitrogen fertilizer rate was about 140 kilograms of nitrogen per hectare, at which N2O emissions were modest on the left, around 0.6 kilograms of N2O, whereas N2O emissions at normal nitrogen rates, the farmers in the Yaqui Valley typically fertilize their wheat at an incredible 300 kilograms of N per hectare or 300 pounds per acre. The N2O emissions at this rate were substantially more, providing a pretty substantial potential CO2 equivalent savings for farmers to reduce their N use to optimal. This also provides a basis for providing carbon credits for N management, which we've been involved in over the past few years. So field scale nitrogen use efficiency is key, and mitigation of a substantial fraction of N2O emissions from cropland could be achieved with a more conservative approach to nitrogen recommendations, such as those based on MRTN approaches pioneered by John Sawyer and other researchers at Iowa State a number of years ago. Now, mitigation could also be achieved with precision fertilizer placement, in particular by identifying those subfield areas within any given field that have consistently low yields. In this example on the right, from an analysis led by Bruno Basso's group, 19% of this field was illustrated stable low yields over a 6-year period based on yield monitors and satellite analysis, such that even either fertilizing less or planting these areas to unfertilized perennials like bioenergy crops or prairie strips, as advocated by Lisa Schulte Moore and others at the Iowa State Strips Project, could substantially reduce the nitrous oxide being emitted from this field and fields all across the Midwest. In this analysis, we calculated that some 26% of fields across the Midwest or subfield areas across the U.S. have stable low yields that very often, more often than not even, are unprofitable, and so could well be managed differently from the main cropping field without any loss of economic return and substantial climate benefit. So let me turn now to the third, circle back to the third negative emissions technology in agriculture and remind us of the central importance of BECCS, bioenergy, in 1.5 degrees C scenarios. And I'll point out that the IPCC has noted that the bioenergy use in these 1.5 degree consistent pathways with or without BECCS is important. So we're not just talking about carbon capture and storage when we think about the benefits of bioenergy, but we're also thinking about fossil fuel avoidance and as well the carbon capture that occurs in soil when these crops are planted. Then I want to share with you for just a couple minutes the results of a 10-year experiment at the Kellogg Biological Station that was just published. And this is describing really the first long-term empirical test of alternative bioenergy crops and their potentials for climate mitigation. Now, I'm not going to describe the experiment in any detail here, but just point out that we examined crops along a diversity management gradient ranging from continuous corn to restored prairie, with the aim in part of providing realistic measured life cycle analyses for these. Almost all analyses up to now, at least in a comparative sense like this, have been done with modeling rather than with measurements. And what we found was, in terms of emission reductions relative to gasoline, that all of these crops met the RFS standards for advanced biofuels. And a few were even net negative. The successional system and the restored prairie had greater than 100% reductions relative to gasoline. And interestingly, the benefits were similar for electric vehicles. And this turns out to be the case because there's a lot of waste heat produced when you generate electricity, almost as much as when you, as the energy that's expended when in a biorefinery, the glucose is converted to, or the biomass is converted to ethanol or some other hydrocarbon. There's also a fair amount of embedded energy in the batteries of electric vehicles. But in any case, the surprise here is that electric vehicles, in a straight up comparison, were not dissimilar to the internal combustion vehicles. But for the ethanol fueled vehicles, the energy benefit or the climate benefit relative to gasoline substantially increased with carbon capture and storage. And this is because about 48% of the biomass carbon coming into a biorefinery can be captured. The remaining carbon is blown out the tailpipes when the ethanol is burned, but there is a substantial fraction that can be caught at the biorefinery. But as you can imagine, with electric vehicles, almost all of the carbon can be captured in the generating facility, which would explain the additional benefit of the carbon capture and storage for the electric vehicles. Almost a bit more than 90% of the biomass carbon can be captured in an electric generating facility. Okay, so where does this leave us? How far do these technologies get us to the 100 to 1,000 gigatons of CO2 needed to remove by 2100? Well, we can calculate the impact of any given practice change in agriculture or forestry for that matter
by, for any given practice, understanding the range of values that are provided by that practice from measurements at a particular field site, weighted towards results from long-term studies, because very often it's the long-term studies that provide us the sufficient period over which climate or weather, year-to-year climate can accurately give us a picture of what we can expect over the long term. And for that practice, we can also calculate the areal extent over which that practice might be extended, weighted to avoid double counting and opportunity costs, and then use Monte Carlo simulation to estimate uncertainty based on ranges. For example, for continuous no-till, we know from many studies across the US that the local rate is somewhere around 1.6 tons of CO2 per hectare. Could be applied to 55 million hectares across the US for an annual total of 86 million tons, probably for 40 years before it saturates, giving us an end of year total as similar. And we can do this for the dozen or so advanced cropping practices that can realistically contribute. And the top 5 are listed here: winter cover crops, continuous no-till, diversified rotations, manure management, and advanced nitrogen management for nitrous oxide abatement. So putting this together into a composite picture to combine with other land management practices, we discover that we can remove somewhere around 72 gigatons of CO2 equivalents by the end of the century, which is a pretty substantial amount. That increases appreciably by about 50% when we add in carbon capture and storage technologies, which we can expect, I hesitate to say hope, which we can expect to have in place by 2050. And this is probably a pretty good segue to Dan Sanchez's talk. So I'm going to stop here with some conclusions that I'll leave up for you to read rather than read them, and leave this for any questions that you might have for the next 5 minutes or however long I've left for questions. So thank you.
Fantastic, Phil. That was really great and just right on point for what we were hoping for you to discuss today. So thank you so much. There has been a few clarifying questions in the chat, and just to clarify for everyone, there'll be a longer discussion period that will include you, Phil, after the panel. But I do want to get to just a few of these clarifying questions. So one question from Ellen Moss: what depth for the soil carbon % increase at KBS?
So for the KBS numbers, the numbers are effectively to 1 meter depth, because we can't document any change below the AP horizon, below 25 centimeters, 30 centimeters.
Okay, great, thanks. And then a question about the comparing conventional no-till and cover crops. Was it just no-till and cover crops as separate treatments, or was there a treatment in which no-till and cover crops were combined?
No, they're separate treatments, which raises a really interesting potential for combining them and perhaps getting an additive effect, which we haven't explored. I would love to be able to say that we have explored that, but we weren't that prescient. We have cover crops in a different set of different experimental treatment than our no-till.
The next study.
Yes.
And then a question from Bill Gutowski: what is the lifetime of nitrous oxide in the atmosphere? For example, CO2 is on the order of centuries, methane is much shorter. How about nitrous oxide?
Yeah, the lifetime of nitrous oxide is around 114 years, which is why in part it has a higher global warming potential than methane, for example.
Okay, great. And then there's a question, Charles T. Anderson said I don't have to ask it, but I'll ask it for the benefit of the group. Can you clarify how the different cropping systems relate to electric vehicles? Let's see, it just disappeared from my chat again. Is the biomass used to produce electricity in the Gelfand study?
Yes, the biomass is used. So the biomass is either effectively either taken to a biorefinery where it's turned into liquid fuel, or it's taken to an electric generating facility where it's just burned.
Great. And here's a question I really love from Michael Schopenhauer: why choose the energy intensive ethanol pathway and not biogas?
Well, biogas is a potential.
Mm-hmm.
We have chosen to go with the liquid fuel, largely because of it's being necessary for the infrastructure needs that we now have in place across the U.S. for vehicles.
Wonderful. Well, thank you again. Please join me for a virtual thank you for Dr. Robertson for his excellent talk and contributions to the discussion here. We'll move now to the panel that includes ISU faculty and a postdoc here at Iowa State. I'm excited to welcome my colleagues here to join us for 2-minute responses. And also there'll be a discussion following the set of 2-minute responses, and Megan Anderson, who's a ISU Extension crop agronomist, field crop agronomist, will help me manage the chat as we move into the discussion. So our first panelist will be Dr. Stephen Hall from the Department of Ecology, Evolution, and Organismal Biology. Stephen.
Great. Well, thanks, Dr. Robertson, for a very engaging talk. There were a couple of themes that really resonated with me. And the first is really that sort of the scale and context dependence of the different levers of agriculture's impact on climate, right? The idea that we really need to, even dial down to the subfield scale to understand which interventions may be most effective in a given context. And I think particularly locally, we have some good evidence here from the poorly drained soils characteristic of the Des Moines lobe that in fact nitrous oxide can have especially high leverage on the overall climate forcing of the system, and we might get even more overall climate impact by focusing on N2O as opposed to soil carbon gains. And I guess the second point I'll make too is that we as a community should really watch out for unexpected feedbacks with changes in different aspects of these cropping systems. For example, combining practices such as no-till and cover crops, we have to consider how they affect both levers of the carbon balance of soil, not only inputs from plant production, but also decomposition fluxes, because we can see some interesting surprises that may in fact limit carbon gains that we would otherwise expect. And some work by our group and others has provided evidence for that. So I believe maybe that's my 2 minutes, and I'll be quiet.
Wonderful. Thank you, Stephen. And next we have Chao-Kun Liu, Dr. Chao-Kun Liu, also from the Department of Ecology, Evolution, and Organismal Biology.
Yeah, thank you, Dr. Robertson, for this informative presentation. I very much appreciate Dr. Robertson's advocating for reducing other greenhouse gas emission as a potential way to save carbon dioxide. So when we put much emphasis on carbon removal, increase nitrogen use efficiency and reduce nitrogen loss, especially through nitrous oxide emission, is something I think we need to pay similar attention to. So like when we look at a farming practice that helps sequester more carbon into soils, but if this practice stimulates nitrous oxide emission, it should be a red flag too. So, I mean, when we assess and identify farming practices that could help climate mitigation in agriculture, we should consider the co-benefits and the trade-off of multiple greenhouse gases. So as an ecosystem modeler, so when I do my work from historical land cover data in the Corn Belt areas, we also see those like corn and soybean acreage increases over the past decade. The share of continuous corn increased, and the Corn Belt has expanded northwestward to Dakotas and Minnesotas. So all this brought more economic profits, but they also led to profound changes in soil carbon stock. So I think in addition to capturing and removing carbon from the atmosphere, reserving the existing carbon stock in soil is also very important. So we should be cautious in taking those farming practices that could result in carbon loss or trade carbon for crop or bioenergy production. Yeah, thank you.
Wonderful. Thank you, Dr. Liu. And next we have Dr. Marshall McDaniel from Agronomy.
Good morning, everyone. Thanks for inviting me, Dr. Schulte Moore, and I've enjoyed Dr. Robertson's talk, and I'm happy to be here. I took a few notes, and not just on Dr. Robertson's talk, but I thought it was interesting. My engineering colleagues called it a carbon cube. And in ag systems, we don't think of it as a cube, but rather it's something dynamic. It also needs to be, that carbon needs to be released, or the nitrogen that's attached to it. So that was one thing I wanted to mention. And then I also really enjoyed Dr. Robertson pointing out that fertilizing at agronomic optimum nitrogen rate is where you see the N2O emissions really take off. And actually work by Dr. Mike Castellano and others have shown that that's actually where we see the greatest increases in soil carbon, is when corn is fertilized to agronomic optimum nitrogen rate. And so I think what that tells me is that there's a lot of relevance to soil fertility and really dialing in and understanding where and how much nitrogen to apply to ag systems, both for the N2O mitigation, but also increasing the soil carbon, or the soil carbon cube. And I think that's all I had.
Wonderful. Thank you, Marshall. And next we'll move to Dr. Suraj Upadhyaya, who's a postdoc in natural resource ecology and management.
Thank you. Thank you, Dr. Phil Robertson, for the great presentation. Two things that I like to focus from your talk. One is carbon credits that you talked a little bit. And then I believe that this provides a lot of opportunity for Iowa farmers to get an extra income. And then through the Iowa Farm and Rural Life poll, we try to understand farmers' opinions about carbon and biomass markets. And then we found that majority of the respondents are either positive or uncertain about those markets, like biomass markets or carbon credit markets. And then I think that we need to come up with some sort of extension and outreach strategies to inform those farmers who are in an uncertain spectrum, so that they can participate or get engaged on those type of market-based incentives. Another thing that you discuss a lot about cover crops, which are more like adaptive behaviors to climate change. And then recently, I, along with Dr. J, conducted research looking into 2020 farm poll data on what are the factors that affect farmers' adaptive and maladaptive behaviors. And then we found that stewardship motivations of farmers was highly correlated with farmers' adaptive behaviors, like cover crops and no-tills. So I think, like, if we can come up with some sort of extension or outreach that can focus on farmers' stewardship ethics, then we might be encouraging them to adopt more adaptive behaviors like cover crops and no-tills. That's all I have. And if you want to know more about Iowa Farm and Rural Life poll, you can look into the link on chat. Thank you.
Wonderful. Thank you, Dr. Suraj. And next, Dr. Dara Wald from the Greenlee School of Journalism.
Hi, thank you. Dr. Robertson, I really appreciated your presentation. So I spent a lot of time thinking about how we engage with people to get them to behave, right, to act. And one of the things that I think we need to remember, and that I kept sort of thinking about when we started talking about, emerging technologies and engineering crops, is that any of these technologies or management strategies that we're talking about are going to occur in places that are already peopled, right? Where people live and work and act, right? And so we need to think about how those individuals respond to the kinds of actions we're asking them to engage in, and understanding what the values are and the beliefs are, and how the kinds of strategies that could get us to reach these really important targets, how they align with the beliefs and the values and the vision that people have in these places, that trying to find ways for those beliefs and values to align with the kinds of strategies that we're talking about, finding those synergies is really important. And so thinking about how that process could develop, how you could engage in a way that is effective and recognizes what people need, what the trade-offs are, right? What are the benefits to these places and to the people, and trying to find, as some of the sea change folks have been talking about, right, values that both value the environment, but also the people and what they need and want. And trying to find ways for those synergies to happen, I think, is really critical. So I'm excited to continue the conversation. That's all I have.
Wonderful. Thank you so much. And now I would invite the audience to post their questions either for Dr. Robertson or for our panelists in the chat. And Megan Anderson will help in terms of conveying those questions help me convey those questions to the panel. So Megan, do we have one queued up right away?
All right, we have a lot of good questions. Can you hear me all right, Lisa? Okay.
Yes, great.
All right, so the first one that I wrote down here that came through the chat was, what are the main issues in terms of communicating the benefits of negative carbon emissions? How much can be done with policy and how much is a matter of communication with all stakeholders?
Wow, big question, really great. Dr. Robertson, do you want to take the first crack at that?
Oh yeah, I think it's really interesting that in both Suraj and Dara's comments, people came up, and I didn't talk about people much at all in my talk. And this, of course, is the missing half of this equation, is how to not only communicate the necessity and the potential for agriculture to participate in real solutions. And most people don't have much of a clue about that, apart from carbon sequestration and soil. But also, how do you motivate people to buy into solutions? How do you motivate landowners? And I say owners rather than farmers, because as we all know, a lot of land that farmers farm is rented. And so the control over what actually happens rests with those making the contracts. And so it's not just a need to inform and motivate those who are actually on the tractors, but also those who own the land, and to think about what they might prefer to see. And so I think communication is hugely important.
Wonderful. Dr. Wald, Dr. Abadiah, would you like to respond to that at all, since you're our human dimensions specialist here on the panel?
I mean, I would echo with what Dr. Robertson said, right? Robertson said that this is the second part of the equation, right? And I was thinking a lot this morning before I came about sort of, there's a difference between encouraging processes or management strategies that support existing visions, existing needs, and existing values. And I think that's actually a much more effective strategy and more ethical, right? Thinking about what people need and what they want, right? Because there are going to be trade-offs in any strategy that we try to encourage, right? There are going to be trade-offs, there are going to be winners and losers. And so thinking obviously we want no one to lose, right? We want this to be a win-win situation. And so thinking about what those folks want, what their existing vision, their needs, and their values are, is going to be more effective than trying to convince folks that they need something that they don't want, right? And so I think we need to really think very carefully, not just about the messaging, right? That's part of communication, but I think shifting the focus to really understanding, and building on the work that Lisa and Jay Arbuckle and others at Iowa State have done to really take the time to understand what people want. And trying to match any strategies that we're trying to promote with the desires and for sort of the future of the land and these places and the values of the people who are already living there, I think is a much more effective strategy. And so I agree it's a fundamentally important additional component of this conversation.
Wonderful. And Dr. Suraj?
Yeah, I agree with Dr. Dara. One of the things that I want to focus is that the communication and then the expectations should start from the farmer side than the researchers or communicator side. So message, what type of message they want to know, what type of problem they want to address, that should start from the people. And then, like Dr. Dara mentioned, people is the major component of the equation. So yeah.
Good. Wonderful. So Megan, I see there's a lot of popularity for Alejandro's question. Can you read that for us?
Yeah, well, I was going to go to that one next anyway because of all the plus ones. But the question is, can the speakers or the panel please comment on the exact metrics that they would recommend to policymakers in order to track actual carbon or greenhouse gas removal at the farm level? And the key is at a manageable cost.
Okay. Does somebody want to volunteer for that? Go for it, Phil.
No, I think Joaquin had her hand up first. Go
Okay.
ahead, Joaquin.
Wonderful. I can't see everybody, so thanks for pointing that out.
Thank you. Yeah, probably I can say something about that. I think people have different focus and interests they want to see. As an ecosystem modeler, because I see spatial heterogeneity of those climate conditions, the soil properties, the landscape characteristics, and farmers' choices in different management. And they together could affect crop production, farming benefit, or economic profit, and the soil carbon sequestrations, but possibly in a quite different way. So in our one of our studies, we have used one variable or term called agricultural carbon footprint. That is how much soil carbon change is accompanied by per unit crop production gain. So I think that this concept could be expanded to like greenhouse gas footprint or other like carbon footprint in bioenergy production. So we put crop production with the ecosystem consequences together. So when we do such evaluation, we may generate a variable that both group of like farmers, policymakers, and our society have interest in. So yeah, that's just my 2 cents.
Wonderful. Thanks. Anyone else like to respond to that question on the panel?
I'll take a quick stab at it. This is a $64,000 question right now that various carbon markets are grappling with. There is an enormous amount of interest in the private sector to find tools that can document soil carbon change at the farm scale cheaply with some veracity. There are, at the other end of the spectrum are those who think that this is largely a fool's errand because of the difficulty, the technical difficulties of doing so in a verifiable way at that scale, with all the variability that happens across fields. My own opinion is that we would be better off paying for practice change than we would be for actual carbon credit, carbon gain in any given field. If we know from the science and from modeling a particular field that we can expect this field on average to have an increase, then there seems to me to be diminishing returns in trying to trying to measure carbon change physically, and rather we should just trust that in aggregate we're going to get as a society benefits by paying farmers to adopt certain practices or allowing farmers to be paid for certain practices.
Great answer. All right.
Can I jump in real?
Go for it, Stephen.
Go ahead, Stephen. You go
And
first.
following on to what Phil said, I think nitrogen rate, as Marshall and others have mentioned, needs to be a really key component of that. And with respect to some predicted agronomic optimum, I believe, as Mike Castellano mentioned in the chat, as we know that this is variable. So some matrix of those practice changes relative to the individual environment.
Yeah, I was actually going to tie that into Mike's question as well. I think this is kind of an ideal future, right? For me, I see a combination of we're going to have to do some soil sampling and greenhouse gas sampling to do verification. We know those properties vary in time and space, but Mike brought up the MRTN, the maximum return to nitrogen online tool. And like he said, that's a great start. But I think we need to push forward with more soil fertility measurements to pin down that agronomic optimum nitrogen rate, but also not just measurements, but modeling is going to help, and remote sensing and some things that aren't as onerous to do, like soil sampling and greenhouse gas measurements, although they're getting easier to do. But that's down the road, 5-10 years from here. I think some of the technology is still developing.
Wonderful. Thanks. All right, Megan, how about another line of questioning?
All right. Well, there are a lot of really good questions. So I'm going to kind of tie two together that I think are related right now. So somebody asked, what happens if a landowner uses these new practices for a significant period of time, but then makes an abrupt switch back to maybe something like plowing are all their gains totally lost? And then someone added to that and said, how do you account for potential reductions or changes in carbon over time that happen maybe not even because of the farmer's fault, because of climate change?
Great questions. I think Phil addressed some of it when he talked about, in aggregate, right? Looking at practices and assessing in aggregate. How about that first part of the question though, Phil?
Yeah, so I mean, that's an excellent point. And of course, carbon is at risk of being lost again, carbon stored in soil, which is, this is where policy comes in, and the policy instruments that need to ensure that the carbon once stored is kept. And this, this comes back to an earlier comment that I think Jiaqun Liu made about conserving existing carbon as well. That is avoiding the release of carbon in wetlands, for example, or in peatland soils. And it's, there are ways to do this, right? We have ways to whether it's through long-term contracts, or whether it's through penalties that are put in place for releasing carbon in the same magnitude of storing it, or some other means. This really gets into the policy realm. I will also say that other practices like N2O abatement, molecule of N2O avoided today never has the opportunity to be emitted again, and so or to be reabsorbed, and so that's a permanent change. So some are permanent, some are not, but those have to be considered in the grand scheme of things for sure. The same with trees, right? Storing carbon in trees is a risky proposition in some environments.
Great.
Okay, so since you brought up nitrous oxide, there was a question that I think will be a quick answer, which is, has similar nitrous oxide loss, I assume, work been done on perennial forage crops?
Yes, and a fair amount of work at Iowa State, in fact. And we know that because it's so related to nitrogen availability, and perennial forage crops, at least non-legumes, have very tight nitrogen cycles, that there's actually very little nitrogen loss, very little nitrous oxide loss from these crops, whether they're grown for forage or for bioenergy. Legumes, on the other hand, alfalfa tends to have very high nitrous oxide emission rates because it fixes nitrogen. It creates its own fertilizer in that way, and it's one of the reasons we grow it, is to provide that nitrogen. Cover crops are an interesting story because we don't really know the complete story for all cover crops yet, but certainly leguminous cover crops, which are grown in part to improve soil fertility, will likely release more N2O when they're plowed down. So that's one of the trade-offs that I think Stephen was referring to earlier when we think about the practices. Growing leguminous cover crops to capture carbon, which they're very effective at, may not save any N2O and may release more N2O, depending on the total fertility level.
Wow, it's complicated. Would anybody else on the panel like to respond at all or answer the question before that one? Are we good? Okay.
I think it's complicated, but it's also manageably complicated. We know a lot about these systems, and we can predict where many of the trade-offs are now.
Thank you for clarifying. That's an important point. Megan.
All right. A question that perhaps multiple people want to jump in on. Are there areas of the country or particular soils where we can sequester more carbon with different management practices?
I'm happy to start if you like, Lisa.
Let's see. I don't see anybody else with a raised hand, so go for it, Bill.
So in general, from theory, the capacity of a soils to hold carbon is related in part to the amount of carbon it's lost in the past. And probably the most, the part of the country, the part of the US that has lost the most carbon is the southeastern US. Cotton, which has been grown there for, 200 or 300 years now, most of those fields are that are now being used for cropping are being grown on subsoil. A lot of the topsoil has eroded, and so that means a lot of the carbon has been lost. Likewise, on individual fields in Iowa, for example, in the Midwest, where you will find the most capacity for carbon absorption or sequestration are on portions of fields that have lost the most carbon. So eroded hilltops, for example, will gain carbon much faster than will downslope areas. And so, yes, there are differences in a soil's capacity to store carbon. There are large-scale geographic differences. There are also very small scale topographic differences.
Marshall, do you want to jump in and talk a little bit about what you found here in Iowa and across the Midwest?
Yeah, Phil's plug was almost perfectly lined up. Yeah, so we published a study. Stephen Hall was a co-author on this from soils in north central Iowa and southern Minnesota in the Des Moines lobe, that the back slopes recovered in carbon the quickest when planted in CRP, Conservation Reserve Program, so perennial grasses, and recovered both more consistently across the landscape and then at a faster rate than other landscape positions, just as Dr. Robertson said.
Megan, can we maybe get another human dimensions question, or there's one about encouraging students?
Yes. Okay, we can go with the encouraging students one, but then I want to ask the one about landowners as well. So do any panelists have advice related to encouraging student engagement, particularly students that are neutral or maybe leaning toward not caring so much about sustainability, or engaging people of all ages who dismiss the environmental movement?
Tara, I'm gonna pitch that one to you.
Sure. So I think I want to say, yes, apathy is a big challenge. But one of the things I think about a lot is that we sometimes have, we have this dichotomy of people who don't care and people who really care and are really upset, right? And engaging both of those groups is really important. And so, yes, I can talk about folks who are apathetic as well, but I also want to remember that we don't want to forget the people who are really angry as an important sort of stakeholder group as well. So in terms of engaging folks who are not interested, that one is particularly challenging because trying to figure out who they are, right, first and foremost, is hard. Like, how do you engage someone who's not showing up for meetings and you don't know who they are, but they don't really care, right? That's challenging. In the case of students, it's a little bit easier because you sometimes have a captive audience. And so one of the things to think about is what drives them, what motivates them to act. We know that people are social creatures, right? If anything has highlighted that, the pandemic has highlighted how much we need other people. There's a lot of really interesting studies on social norms, especially among students, right? How we can get students to identify and behave in ways that their peers are acting. So even if they aren't necessarily engaged, if you have student leaders on campus who are engaged in sustainability, talking about those students and what they're doing actively to engage with sustainability in creative and innovative ways can be the best way to get students to pay attention, right, to their peers and what their peers are doing. I certainly know I'm not a cool example of what sustainability necessarily myself, but my students look to each other very much. And so that's one interesting way to think about it is through norms. The other thing to think about is what are the values and what are the beliefs that these students have about sustainability? What are the potential barriers there? What do they dismiss when it comes to the things that you're trying to get across? And if they're dismissing it, right, what is the reason for that? What do you think are the barriers to getting them to act, right, to create the kinds of habits and actions and activities that you'd be interested in trying to engage in? So doing a little bit of work to try to talk to and engage with students is maybe a really good, another way of trying to figure out what motivates them, what would motivate them, instead of trying to give them a message that you think might appeal to them.
Excellent, great answer. Thank you, Dara. So this will be our last question before the break. So Megan?
Oh gosh, so much pressure. Okay. There's been a lot of really good discussion, questions about kind of this landowner, farmer sort of interaction, right? So kind of comments about how landowners might be involved in implementation of these strategies? Can it pay for a farmer to make these changes? With many small farms struggling in the environment that we've been in recently, is implementation truly possible? And then is there a social support system, or do you have any thoughts on a social support system to maybe help farmers adopt practices and resist social pressure to conform to current practices? So I think it'd be interesting if anybody would like to speak to that kind of landowner farmer cost and social pressure dynamic.
Wow, so many really great questions. We have so little time. I'm going to pitch that one to Dr. Suraj for a 1-minute answer before we wrap up for a short break.
Yeah, one thing that the way to minimize costs for the landowners or farmers is encourage them, provide the market-based incentives, like money-based incentives, like carbon market or market for biomass. And then I have seen that carbon credit is getting familiar in agriculture system. So that might provide extra income for farmers that can minimize their cost or cover the cost. And then at the same time, that can relate with the earlier question, like what if they were doing practice for a long time and then move to some other maladaptive behaviors? If farmers are actively participate on carbon credit market, then that will encourage them to continue the same practices. So that can, that can help farmers and landowners to continue the adaptive behaviors at the same time, minimize the cost. So that's my response.
Super.
Thank you.
Well, thank you everyone for sharing your great knowledge and fantastic enthusiasm for these topics. And also thank you to the attendees for all of their wonderful questions. This is a great conversation. I wish we had more time, and we do after a short break to get into sort of engineering aspects regarding carbon removal. So please, before you take a short break, join me in giving a warm virtual thank you to Dr. Phil Robertson and all of the experts on our panel, as well as Megan for helping me moderate the discussion. See you back here in 10 minutes.